So this is lecture 12 today, and of course the silently. Okay, it's lecture 12 today, and of course the last lecture before the Christmas and New Year holidays. From the point of view of this course, this also represents the end of the core material of the course. So, core material. Of course, that's in lectures 1 to 12. Is lecture 12 today. We've got 2 more lectures after the New Year, for the exam break, and those lectures are advanced material, or optional advanced material. So optional advanced material. It's 13 and 14. And this is going to be, lecture 13 is going to be on something called Kolmogorov complexity. Algorithmic complexity. And lecture 14 is going to be on something called algorithmic randomness. What the optional advanced means is that this material will be needed if you want to get a 10 for the course, in which case it will be examinable in the oral exam. But if you're not aiming for a 10, well, you're still welcome to look at it. I mean, there's nothing wrong with also having material, but you don't need it. So you only need. So if you're happy with what you've learned in lecture 1 to 12, and you're happy to go away without a 10, then you're very welcome to attend lectures 13 and 14, and obviously want to get to know the material. Also, the other difference is that up to this point, everything is potentially examinable in the written exam. So the written exam. That plus exam. So also, I think again the theory side will be covered in the oral exam. And this is for people aiming for a 10. And so also after the New Year, there are 2 exercise classes. The first exercise class will be on the material we covered today, and the second exercise class will be probably a revision exercise class in preparation for the written exam. Okay, are there any questions on that? So this is just the logistics part, or something more general logistically. Okay, we'll go over to this side and we'll start material today. So today we're going to look at real number computability, or computing with real numbers. And in a sense, this is really one of the this is one of the main motivations for looking at this work, this body of material on type 2 Turing machines and computability with continuous data, because this is an important application. And in order to be able to deal with this application, we can set up the machinery to do this. So, yes, obviously a useful thing to do, and something that's done in science, all science, that one computes with real numbers. And in usual programming with real numbers, one uses floating point arithmetic in one form or another. The original floating point that had a certain level of precision, and then what's called double precision and triple precision, quadruple precision, so all versions of increased precision, but so standard programming languages real numbers uses floating point with a fixed degree of precision, which could be what we precision or higher precision. Fixed degree precision. This is nice in the sense that the arithmetic for floating point numbers is built into hardware chips, so it's very, very efficient. So it works fast, and for a lot of everyday purposes, it's perfectly accurate enough, because although you have a fixed degree of precision, that precision is given essentially in a version of scientific notation. So you have a fixed, in scientific notation, you have the antissa, as it's called, the significand, and the exponent, and you have a fixed number of bits for the significand, but it's quite a lot of bits. It gives you, I think, so I remember, even ordinary single precision floating point arithmetic gives you something like 20-something decimal digits of precision in the significand of the scientific notation. And then you have an exponent that can range from minus something very large to plus something very large. So you have good precision and a very good range of numbers that you can cover with it. However, for some applications, so because you've got a fixed degree of precision, you're essentially representing numbers as rational numbers. And for some applications, the round-off errors that you necessarily get if you divide by 3 or something, or something like that, you're not going to represent 1/3 exactly. The round-off errors eventually multiply and can make results completely unreliable, especially if you sort of iterate sensitive operations a large number of times. So for everyday purposes, for most purposes, this is okay. For most everyday purposes, this is okay. But sometimes it leads to unwanted errors, rounding errors. And these errors can be also hard to predict in advance. So people have applied such algorithms just trusting the results in situations in which that was not a good thing to do. So I think maybe back in the 60s, so a long time ago, people first realized that there's another approach, and that's something that has since become known as exact real number computation. So different approach. And
And the idea is basically it does what it says in its name, that you represent real numbers exactly as infinite streams, so infinite sequences of data, and you can never store an infinite sequence of data, but you can implicitly work within infinite sequences of data using programs that will, given any finite number of bits, will generate the next bit, so to speak. So programs that generate the sequence as and when you want demand, as you need it. And the naive idea would be just to represent, just like a real number is represented as an infinite. In our everyday of writing real numbers, we represent real numbers as infinite decimal expansions, or we could simply put that decimal expansion in the stream, although there are problems with that, you'll see. But that would be the basic idea. So exact real number computation, so basic idea. Use infinite streams. In other words, only words, as we're looking at, to represent and compute with real numbers exactly. Exactly means, again, without rounding. And it's a very nice idea. And people have built this into programming languages in various different ways. Actually, it raises quite a few quite subtle questions in how one computes, and it's still an active topic of research. And in fact, it's a topic that is one of the areas I'm interested in. And if anyone's interested in sort of recent research on this, let me mention. So earlier this year, Professor Bauer and I, together with somebody called Sewon Park, who is a collaborator from South Korea that now works in Japan, and we submitted. So just in case anyone's interested, you can find this on the archive. EEG, imperative language. Real number computation. This paper is about a programming language that's designed for this kind of computation on exact reals. Actually, in the paper, you won't see any infinite streams representation of real numbers. The whole point of the programming languages is to abstract away from it and just have like an abstract type of real numbers that you can program with as if they're exact. But the implementation we have of our language, which is something Professor Bauer implemented, does use infinite sequences, that does use the streams in it. And essentially the mathematics that we're going to do today is the mathematics that underpins applications like this. Okay, so the very naive idea, the most naive way of doing this would be, and I was already using this as motivation 2 lectures ago when we first considered not written here, but when we first considered the topic of computing with continuous data, I started off motivating it by looking at representing real numbers using infinite decimal expansions. So let's go back to that idea. We're going to see that perhaps surprisingly, this idea is not actually a very good idea, or it doesn't quite work for being able to compute real numbers exactly. There's a problem with it. So fixing the problem is going to be basically the goal of the lecture, and then we'll see some properties that
the good properties that we get from once we fix the problem. So we go back. Let's go back. Oh, what's a good pen? Go back to the idea. To the idea of representing real numbers as limited words. So via, I mean, you could use any base for this. You don't need to use base 10, but because it's familiar, let's use base 10. So via infinite decimal expansions. The same idea applies to any other base B, where of course the base needs to be at least 2 to represent real numbers. And the same problem that we're going to, or analogous problems to the one we're going to identify also arise for other base representations. But other base B greater than or equal to 2 representations. Analogous. If we're just doing things in base 10, then so for example, pi would be represented by excuse me. Pi would be represented by the obvious thing. I use the decimal point because it's English lecture. Right, and so on. And we'll just use the most naive representation. So minus pi would be represented by minus 3. Next. So what we will consider are omega words over the relevant alphabet. Only the words over. Oh, we've got the hello. What's your view on topology this week? In general, or I don't know. Just last week you said something about topology and then out of the room. So
I stand by my statement. So
okay. Anyway, let's carry on for the moment. We don't want to expose you too much on the video. It's not really bad. So anyway, we have omega words over the 10 decimal digits, decimal point symbol and minus sign. And for an omega word to be well formed, we can make requirements like there's at most 1 minus, and if it occurs as the first symbol. It occurs as the first symbol. We want to represent real numbers by always an infinite expansion. So we're always using an infinite word. So we should require there's exactly 1 decimal point. Exactly 1. And that's actually enough. Because we're forced to have infinitely many digits after the decimal point with these 2 rules. We might get something that would look a bit funny, minus 0.0000, something like that. But I mean, obviously we can understand that as minus 0. Well, as 0 in this case. one representation. So that's enough rules for knowing a word representing a number. So it's not enough to represent numbers, we want to be able to compute with them. We want to be able to compute with them exactly. And so that means we would like an algorithm that essentially we're giving ourselves names for real numbers. Names, it now means an omega word representing a real number. We would like an algorithm on omega words we would like algorithms for the usual operations. Right? We would like an algorithm on omega words that takes two omega words for two real numbers and finds us an omega word for the sum of the two real numbers, or for the product of the two real numbers. And sadly, such algorithms don't exist. So that's the problem with this representation. Can't add two real numbers, can't multiply two real numbers. And in fact, to see that most succinctly, what we're going to show is that with this representation, we can't even multiply a single real number by 3. Okay? So this is not a good representation. That's kind of intuitive, but it's the representation we use. It's the decimal representation. No multiplication by 3 algorithm. Might need to come in. So why not? So let's actually prove that there is no multiplication by 3 algorithm. It's not particularly difficult. So we'll suppose there is such an algorithm and we'll reach a contradiction. So to show this, and suppose the contradiction this section of algorithm maybe I want a bit more space there. So such an algorithm will be a type 2 Turing machine that takes omega words out of this alphabet as input and produces an omega word out of this alphabet as output, with the property that whenever it's given a representation of a real number, it gives us back a representation of the real number that is the original real number multiplied by 3. That's what we would like the algorithm to do. We're assuming that there's an algorithm that does that for contradiction. So suppose, consider, so there exists such an algorithm, i.e. by algorithm we mean a type 2 Turing machine. So consider, let's call it M. So consider what M does on the input. So let's give it a particular input. We'll give it the input, which is the unique decimal expansion representing the number 1/3. Okay, so the 3 to the omega here, I know one normally puts the dot on, but anyway, the 3 to the omega means we continue with an infinite number of 3s.
So then M produces the output. So what output does the machine M give if we give it 0.33333333 as its input?
1.
Which needs to be an omega word.
1.000.
Okay, so it produces the output 1.000000, and so on to the omega. Is there another possible behavior it could have?
But only 0.9.
It could also output, so it will output exactly one of these two. It will either produce 1.00000 or 0.99999. So do one of those. And we're going to show that either case leads to contradiction. So let me consider in the notes, the later notes, the first case is covered. So let me consider the second case. They're both very similar. So suppose e.g. outputs 0.99. And then we want to see what the problem is. So you're reading, the machine needs to read this input sequence bit, well, I was going to say bit by bit, but it's like decimal digit by decimal digit. Dit, I suppose, dit by dit. And it needs to output one of these. So can somebody see what the problem is?
Find an open neighborhood of one of these two. And then, because this is continuous, the pre-image should be that's
Yeah.
same.
You're kind of jumping ahead in a sense. So, I mean, there's some truth in what you're saying, but you're talking about open in the real numbers.
No, no.
Okay, right. No, good. Yeah, so the implementation needs to be continuous, as we saw last week in the topology on the bare space or the space of omega words that we considered last week, and there can't be a continuous function. But there's a simpler way of saying this in this case, which is the machine at some point needs to decide whether to output 1 or 0 as the first part of output. Actually, if the output 0 depends on our rules, but we might still not be going. It might be eventually going to. So actually, there are other. So with my current rules, there are other things that it could output as well. It could also be just decimal 0.9. So anyway, it doesn't matter. There are a number of possibilities, and it has to decide between kind of giving one at some point a 1.000 or a 0.99999 representation of 0 or 1. And the point is, it can never make that decision, because when it makes that decision, it will at that time only input finitely many, it will only see finitely many 3s. And it doesn't know that the input sequence is going to continue with 3s. It could continue at some point with 0000, or it could continue at some point with 99999. And it can't commit to 1, because if this input sequence dropped lower, then it would have needed to start like this. And it can't commit to 0.9, because if the input sequence goes up, then it would have needed to start with 1. But let's see that formally using the continuity property that we established in the previous lecture. So, by the continuity theorem of the previous lecture, there exists some n such that n outputs 0.9 on any omega word of the form 0.333. Right, this has n symbols, and this can continue just as any other omega word. So the point is, if it's going to output 0.9, then this 0.9 thing, it will do so after it's read some number of input symbols. And once if we look, then any other string that agrees with the input on that number of input symbols, then we're going to get the same initial output. So for any number of this form, we'll still get the number starting 0.9. But so then it will produce an output starting 0.9, also for the input. So if we consider the same initial input prefix of n symbols and n minus 2 threes. And then we continue the input with 99999. So that's the same as the real number 0.333334 for the last digit here. It's going to still try to give us an output starting with 0.9, but of course 3 times this number is something greater than 1. But 3 times the input real is greater than 1, so it cannot have a representation starting with 0.9. So the machine goes wrong. So how are we going to fix this? Does anyone have an idea how we can fix it? Oh, well, before that, just to say, the similar problems hold for any base representation, not just for base 10. So for binary representation, for base 2, again, you can't multiply by 3. For base 3 representation, you can multiply by 3, because multiplying by 3 is just shifting the decimal point one place to the right. But in base 3 notation, you probably can't multiply by 2. But you certainly can't multiply by 5. I think you probably can't multiply by 2. You can think about that anyway. Interesting, in binary representation, you can divide by 3, but you can't multiply. Anyway, there's a problem. So does anyone have a suggestion for how we fix it? Let me think about that while I look to see what the next thing I want to say is. Yeah. Well, obviously we're going to change the representation. So actually a really simple thing one can do is one can, as well as the usual digits, we can also add negative digits. -1 up to -9 as well. And actually, at this point, it's nicer to start working with binary, because anyway, binary was nice to people. So then we would have 3 digits, 0, 1, -1. And then this kind of problem doesn't arise, because it doesn't matter that we start with hang on. Yeah, it does matter that we start with 0.9 in this case, but we wouldn't start with 0.9 if we have negative digits after we've read sufficient amount of the input to know that we're sufficiently close to 1. We give ourselves the starting number 1 because we know we're close to 1. And then if it turns out that actually we're going to end up below 1, we can later use some negative digits to bring our value down a little bit. So surprisingly, that works. But that's not the solution I'm going to present today. The solution I'm going to present today is to look at a different representation of real numbers. I know we've had a very short first part here, but this is really the natural breaking point. So it's 5:02 by the clock on the back wall, so we'll start again at 10 past 3. Okay, so we want to give a better behaved way of representing real numbers. So technically what we're going to do is we're going to define a representation of the set of real numbers as a representation similar to the kinds of representations we've already been considering for like sets of natural numbers and product sets and things like that. Going back to the lecture on representations, I think lecture 3, earlier on in the course, only the difference now is that we're going to represent, so whereas we started off in lecture 3 representing sets by giving them names that were finite words, later we moved to representations where the names were numbers, natural numbers. We're now going to make use of the type 2 machinery that we have. So we're going to consider representations where the names are omega words. So this leads us to the notion of the type 2 representation of the set X is simply using an alphabet sigma is simply so remember originally we had a surjective partial function from the set of words over the alphabet sigma to X. So now we ask for a surjective partial function going to still continue using gammas for representation. So surjective partial function gamma now from the set of omega words over our alphabet sigma. Again, surjective partial function from this symbol to the set X. And again, we say that P is a name or realizer. We intend to use name for an element X in the set X if gamma of P equals X. Find a good such representation of the set of real numbers. And notice that, so in lecture 3, and also when we use, so that's when we use finite word representations, and also when we use natural numbers representations, we had the fact that the only representable sets were countable sets, either infinite or finite. We now have, well, here we've got so this set has cardinality the continuum, the same cardinality as the set of real numbers. We want a surjective partial function, so again, this we can get such partial functions whenever we've got sets that have cardinality continuum or less. So we now can represent sets that are not countable. And as we will see, we can, for example, we can represent a set of real numbers. And in fact, our decimal representation is already a representation of the set of real numbers. It's just not a useful computation. It's not a good computational representation because we can't compute simple functions on it like addition, multiplication by 3 and things like that. Okay, so we have the notion of type 2 representation. Just as we had before, if we've got representation of a set X, a type 2 representation of a set X, and a type 2 representation of a set Y, then we say that a function from X to Y is computable if basically the same conditions as we had in lecture 3. So let's just very quickly, there's quite a bit of stuff in the LaTeX notes, but I'll just go over it quickly for the lecture. So we're given representations, by which I mean reps, but by which I mean type 2 representations. So gamma, well, sigma, so that's a type 2 representation of X, and gamma prime, type 2 representation of X prime. We say a function f from X to X prime is computable if it has, so we want to know what it means for a function from the representing set X to the representing set X prime to be computable, and we can reduce that to the notion of computable function from the set of omega words to itself, and that we know what a computable function is because that's what we done 2 lectures ago when we introduced type 2 Turing trees. So f is computable again if it has a computable realizer. It has a computable realizer G, from which is a partial function acting on omega words.
Excuse me.
Yeah.
Do you want to assert that the function is total? F is F total because you wrote that X.
So sorry, that should be a partial function. Computable. Realizer. Thank you. And computable realizer meant as before, i.e. G restricts to a function to a partial function from domain gamma to the domain of gamma prime. It's an arrow there, it's a partial arrow. So whenever G is defined on a name for something in X, it produces something, a name for something in the set X prime, and also diagram below computes, meaning the composite function is the same. So we have G, we're given any name for something in X, that's something in the set of names for things in X are the elements of the domain of gamma. We take G. That takes us onto a name for something in X prime, but obviously what we want to hold is, here we have now total functions, gamma prime, X to X prime, and here we have function after computing, and this is simply saying that given the name for something in X, we apply G to it, we get. So if we're given the name for an element little x in X, given the name up here and we apply G to it, we get back a name for f of x. Okay. And these are exactly the conditions we had in lecture 3, just the only difference is that we've replaced the set of finite words with the set of omega words. So what we want to do is find a nice representation of the real numbers such that lots of functions are computable in this, the functions we expect to be computable are computable in this sense. Of course, we should generalize if we're looking at addition and multiplication and so on. We should generalize to functions in more than one argument. But I don't do that in the notes, and you can make the generalizations yourself if you want to. And maybe something like that will be done in the exercise class today, or the first exercise class in January. There is one thing that is of interest with respect to type 2 representations that does not occur at all with respect to the original representation, type 1, if you like, representations that we had in lecture 3 and also in the natural numbers representations. And that's that the type 2 representations give us also a notion of what it means for an element of the set X to be computable. Okay, so given, I've already said given representation is gamma and gamma prime, so gamma is a representation, we say X, little x, an element of the set X is computable. With respect to the representation gamma, if anyone complete this definition, or just quench my thirst. But there's a fundamental difference between. Originally, we were looking at representations with finite words, names for finite words. Now we're looking at representations where names are infinite words. And does it mean to say if a finite word, you've got a finite word, does it make sense to talk about is this word computable? It doesn't, because every finite word is computable. Every finite word can be output by a Turing machine, so you simply write a little finite program that outputs that word symbol by symbol. Does it make sense to talk about perhaps an omega word, whether an omega word is computable? Not, of course, it does make sense, because 2 lectures ago, that was one of the concepts we introduced for type 2 Turing machines. An omega word is computable if we will remember, if there's a type 2 Turing machine that doesn't take any input, but just generates the omega word. Okay? So given that, when do you think an element of the set X, of a represented set X is computable? Any suggestion?
There's some Turing machine that doesn't accept me, but produces one of its records.
Yeah, so that's right. But we can use the notion of computable, the computable element, so the omega, we've already defined that. But it's the same as what you said. So if it has a computable name, so if there exists, so if there exists a computable P is equal to the omega, such that P is the name of X, meaning the gamma of P. Okay. So just to, the point here is just to emphasize, we've got basically the very analogous theory of representations to the one we had when we were using finite names for representations. But now, because we're using infinite names, we also have a further interesting concept, which is an element of the set itself being computable. And we've already seen a flavor of that because we've already talked about the notion of what it means for a real number to be computable. And as I said 2 lectures ago, that was the topic of Turing's original paper. Computability is focused around real numbers. Okay, so that's enough about general representations. Let's now give a representation of R, which is a good, of the real numbers R, which is a good representation of the numbers. Maybe just start on the board here. And the idea is we're going to call it or maybe to say the LaTeX notes first define formally the binary representation using binary sequences that I've already told you is not a good representation. And then this representation, then the good representation that I'm going to give. In the lecture, I'm going to skip the bad representation. I think we've talked enough about representations that don't work, and we'll go straight to the good representation. This representation is called the Cauchy representation because it's based on Cauchy sequences. The slightly unsatisfactory thing about it is it's quite complicated. Because Cauchy sequences are slightly complicated. So to give the Cauchy representation, we're first going of real numbers, we're first going to give them, so this is a type 2 representation. We're first going to give a type 1 representation of the set of dyadic rational numbers. So you might remember from analysis in the first year undergraduate, that one can construct reals using formally as a set of Cauchy sequences of rationals. I mean, there are various ways of doing it. You look at real numbers as being given by Cauchy sequences of rationals. In fact, you can restrict to dyadic rationals. Who knows what's a dyadic rational? Yeah. Aha. Yeah. Yeah. So it's a rational number that can be written as a fraction of an integer fraction where the denominator, that's the bit on the bottom of the fraction, is a power of 2. So the first step, a type 1 representation of Q, do I call it little d? Q little d. Q little d equals set of dyadic rationals. In other words, all numbers of the form n over 2 to the n, where n is an integer and, well, m and n are both integers. So, in fact, we did this representation in an exercise class, like in about week 4 or something like this, the exercise class on representations. So we represent a dyadic rational by a finite word. As we write it here, we represent a dyadic rational by a finite word of the form d n minus 1.
So we've got a finite sequence of up to d down to d0, decimal point, sorry, binary point, d minus 1 down to d minus n, where every di is a bit, so it's either 0 or 1. M and n are greater than or equal to 0. And we allow, I'm going to put it, just put an orange square brackets here to make it so the orange is to emphasize it's not part of the notation, but there's a potential minus here in case it's a negative number. Okay. And so it's simply, you read this as a binary integer followed by the binary point from the decimal point, and then the expansion of the fractional part. And I could write out the sum, but I don't really see the need to. It's the usual interpretation of this as a binary natural number. So here we have d0 times 1 plus d1 times 2, all the way up to d n minus 1 times 2 to the power of n minus 1. And here we're simply going in the other direction, so it's d minus 1 times a half, all the way plus, all the way down to d minus n times 1 over 2 to the n, or 2 to the minus n. So the indexing here is given because it gives you the exponent of the power of 2 that is the multiplier for that digit. Okay? Why not write it out as a formula? There's a few puzzled faces. So it represents the sum, but I counting up from n minus 1 to n of di times 2 to the I. Okay. Sorry, it should be counting up from minus n to n minus 1. So it's clear that every such finite word represents dyadic rational because we're simply summing multiples of fractions of 1 over 2 to the n. Hopefully, it's also equally clear that you can represent any dyadic rational in this way by just taking the suitably large denominator and then kind of filling in the rest of the sequence. Does every dyadic rational have a unique representation like this? Yes, no.
0 could be with plus or with minus.
So 0 can be with plus or minus, and I haven't given any rules that say we can't have 0, 0, 0, 0, 0 here, or we could have 1 less 0 or something. So or we could finish off with a tail of zeros here. So they're very much not unique. As I define them, you could not hard with this notation to actually make them unique by choosing a canonical representative, but we don't need to do that. So the dyadic representation, So what I should have done, and let's do that. For this, if we call this word U, yeah, then this will define as QD of U. So the function Q sub D takes the word U and returns its value. It's a dyadic rational.
So in doing this, we've defined the representation, so the dyadic representation is simply this function QD, which maps us from what I'm calling sigma B. It's a surjective representation of the dyadic rationals, where sigma B, where this is it's a representation using finite words over sigma B, where sigma B has the two binary bits, it has the minus symbol, and it has the decimal point. Okay. And it's not defined on all words, because, for example, it's not defined if a word has two minus symbols, or a minus symbol in the middle, or two decimal points, or no decimal point. Yeah, so those are cases in which it's not defined. So now the main thing we want to do is, so this is the type 1 representation of QD. So now we get to the Cauchy representation of the reals, so we now define Cauchy representation of the reals, which is going to be gamma sub c for Cauchy, which is going to take us from omega words over the Cauchy alphabet and give us back the real number. And it's going to be surjective. So this is Cauchy representation. And maybe won't be very efficient with board space, but a good place to start somewhere else. Well, I'm going to maybe I'll. So we're going to define this by saying first what its domain looks like. So we're going to say some subset of the. I guess the first thing to say is what sigma c is. The alphabet is, we have all the symbols we've got so far in wherever it is, sigma b, so 0, 1, minus, and the decimal point. We give ourselves another separator, so it's sigma b, so it will also add semicolon as another symbol, which we're going to use as a further separator. And so this wants to be a partial function, a surjective partial function onto the reals. We're going to say what its domain of definition is. So when it's defined, in other words, what an omega word needs to look like in order to be a name for a real number. So the domain of this partial function, domain of gamma c, in other words, we're looking at the set of all names for real numbers, consists of omega words of the form. And the point is we want a name to be an omega sequence of dyadic rational. Sorry, not an omega sequence, a Cauchy sequence of dyadic rationals. So we require it to look like a sequence of dyadic rationals. So I'm going to start numbering with 0, and we use the semicolon. So U0 is going to be a name for a dyadic rational. In other words, some name from the dyadic rational representation. So something that looks like this. And then we use a semicolon, and then we give U1, that's the next dyadic rational, then U2, then U3, and so on. So we have infinitely many semicolons. Okay. So where
each ui belongs to the domain of QD, the dyadic rational representation, and moreover, so that's just saying that this defines a sequence of dyadic rationals, and we want that sequence to be a Cauchy sequence. And the sequence of dyadic rationals that we get from well, by just the numbers represented by each of these. So QD is U0, followed by QD U1, followed by QD U2, followed and so on. That sequence is what we're going to call a fast Cauchy sequence. So it needs to be a Cauchy sequence, but not only a Cauchy sequence, but one that's fast, which means it has a particular specified good rate of convergence. QD is so this is continuing this sentence, is a fast Cauchy sequence. i.e., it satisfies, that is, it satisfies remember, Cauchy sequence is one that satisfies for any epsilon, there'll be some place within the sequence such that if you consider any two terms in the sequence beyond that position, they'll be within epsilon of each other. What we require here is that actually from any nth term onwards, if you consider two terms beyond the nth term, they're within 1/2 to the n of each other. Okay, so it's converging rapidly, exponentially. So we can say that like this. So for all n greater than equal to n greater than equal to 0, so n is the point that we're looking beyond, and n is somewhere beyond it. If we look at the difference between QD of UN, so the dyadic rational represented by UN and the dyadic rational represented by UN, they are within 2 to the minus n of each other. Okay. So this is now specifying the domain of the Cauchy representation. And now we want to say what we've got a name, so an omega word over this alphabet, 0, 1, decimal point, minus, and semicolon. An omega word over this alphabet is a name, only satisfies this property. And now we want to say what the real number, we need to define the representation of the rules. We want to say what the real number represented by such a name is. So for such a name, P of this form we define. So we want to say what the real number represented by the Cauchy representation is. Defining this function by saying, to this name, we give it this real value. So could somebody tell me what is the real value that we want to give it to P? The limit of the Cauchy sequence. Yeah, very good. So the lim as n tends to infinity of QD of UN, the dyadic rational represented by UN.
Shouldn't we require for all n there exists on n such as this relative was
Okay, so the usual condition is for all epsilon,
Yeah.
there exists an n such that for all m greater than or equal to n, this inequality holds. Okay? But we're strengthening that, we're saying for any epsilon of the form 1/2 to the n, there exists an n, but actually that n is just n itself. So it's a stronger property. We're fixing, we're not just saying from some point on we're within 1/2 to the n, we're actually within 1/2. As soon as we get to the nth term, everything beyond it is within 1/2 to the n, but we don't go beyond more than 1/2 to the n from where we are. So we've got a very fast rate of conversion, specified rate of conversion. And right. And so that'll be useful in the next property. So let's just state some basic properties of this representation. So this is the representation. Yes.
You wrote U and shouldn't maybe P? The U.
So okay, so for such a name P, I'm saying for P, so such a name means a P of this form. Okay, so I'm saying for such a name, for any such name P, and we're expanding P as
yes,
U0, yeah. Yeah, that's say that very clearly. So this is a good representation. Can be the more technical part of the lecture is going to be the third hour, as it sometimes has been in the past. And I think to have things to refer to, I'm going to number propositions as in the lecture notes. So let's not get to dwell too much on the properties, but first one is proposition 12.8. And the first point says, indeed, it is a representation. So for every x in R, there indeed exists a P in the domain of gamma C, such that gamma C so there exists a name that represents that real number x. Okay. How can we see this? How can we see that for every real number there exists a Cauchy representation of this form? So we need to find a sequence of omega words that converges sufficiently rapidly to the real number x. Where these omega words, each of these is one of these finite words represented with either rational.
Well, we already assume that we have the decimal representation of fields.
Yeah, I mean, we don't need to make assumptions. We're just working in the world of ordinary maths. So
Okay, yes.
yeah, so we have a decimal so every real has a decimal representation.
Yes, so, well,
every real, maybe it would be actually more useful to notice that every real has a binary representation, an infinite binary representation.
so I wanted to say that we just the Cauchy sequence is constructed as just taking progressively walking down the ordinary representation, but that doesn't work because some keys are not dietic.
Yeah, so basically you consider an ordinary representation and you walk down digit by digit to get your but you don't start with a decimal representation because indeed then you don't get dyadic rationals. You know, your denominators are powers of 10, not powers of 2. So instead, we start with the ordinary binary representation of a real number, and we simply walk through that by taking longer and longer prefixes of the decimal, what would be the decimal part, but the part beyond the points. Okay. So I hope that's enough for the lecture. If not, think about it, and maybe I'll give us an exercise class. Well, it's given in more detail in the lecture. So the second thing is that if B in the domain of the representation is as above, as before, so namely U0 semicolon U1 semicolon U2, then for any n greater than or equal to 0, it holds that the difference between the dyadic rational represented by U of n and by UN, the entry, that dyadic rational entry in the Cauchy sequence, and the real represented by P is always less than or equal to 2p minus n. Okay, so here we've got any two, from n onwards, any further point in the sequence is within 2 to the minus n. So then, because the points within 2 to the minus n are a closed interval, the limit will also be within the same distance of the same distance from the dyadic rational QD of the event. Okay, so basically follows this one. So just wanted to note that. Okay, so now we have the representation, so I think that's the main point for this hour of the lecture. Once we've got a representation, we can ask what, because it's a type 2 representation, we can ask what the computable real numbers are. We already answered that 2 weeks ago. We defined what a computable real number is. I think we did, using the decimal representation. Maybe we did, maybe we didn't, but I at least talked about it. We've now got a different representation of the reals. But there's a proposition, which is 12.9 in the notes, but I'm not going to refer to this one later, so we don't need the number of the lecture. Proposition is that, so we can ask, we now got what I'm claiming is a nice representation of real numbers. So what are its computable real numbers? So a real number, X, we don't need to name for it. So a real number is computable according to this Cauchy representation, if and only if it is computable with respect to the decimal notation or the ordinary binary notation. Computable with respect to decimal or binary representation. So now got what I'm claiming is a good notion of representation of the real numbers. You can ask what are the computable reals, so which real numbers have computable names. And actually, it's the same as if we use the decimal or binary representation. Okay. Now, I don't prove this in the notes. Maybe Deborah will consider it in the exercise class in January. I'm not sure. It's a very messy result to prove. So it's not, there is no nice proof of this. And one, for those who are sensitive to constructive maths things, one way of saying that is that this is very definitely not constructively true, this statement. So it requires classical logic.
to prove this. For those who, just as a remark, for those who are sensitive. The reason for that is because, we're showing a sort of equivalence to some degree in terms of what's computability between different representations, where one's a good representation and the other ones are not. And constructively, you can't really do anything sensible with a bad representation. So how do we know that this is a good representation? Well, for example, proposition, the function x maps on to 3 times x that was problematic before is computable with respect to, gamma c. This is the function on real numbers with respect to gamma c. Cauchy representation. Now this is very easy to see because we want to be able to take a name that represents a real number x and multiply it by 3. So we take a name like this that represents the real number x. Well, all we need is an algorithm that will take any name for a dyadic rational and multiply that by 3 to give us a name for the dyadic rational. If you multiply a dyadic rational by 3, you get back a dyadic rational, and we just give the name for 3 times that. Yeah, we do an ordinary simple multiplication algorithm. We get a name for the dyadic rational 3 times. And then we could try to return the sequence dyadic rational representing 3 times u0, dyadic rational representing 3 times u1, dyadic rational representing 3 times u2, dyadic rational representing 3 times u3, and so on. But actually, we can't return that sequence. Can somebody see why not? Yeah, the difference is not small enough because multiplied by 3, we're multiplied by more than 2. Well, we're multiplying by a number. So in fact, we're multiplying by a number less than 4. So the differences go up by a number less than 4. So in fact, all we need to do is do that procedure, but drop the first 2 terms from the sequence, and then the rest converges at the right rate. Okay, so it's a little bit of something there, and that's in more detail in the notes. Anyway, is this a spectacular result that we can multiply by 3? No, that's a trivial thing. So what is more relevant is that not only can we multiply by 3, we can add, we can multiply, we can do all sorts of stuff. And whenever you have a sufficiently well-behaved, which almost all functions are, function that's useful in analysis, it will be computable. So in practice, pretty much everything that we want is computable, subject to the following constraint. And this is the theorem that is going to be the main goal of the last hour of the lecture. So I shall state it now and then we'll have the break.
Excuse me.
Yeah.
Just very quickly, and the trigonometric functions computable.
The trigonometric functions are computable, yes. Indeed. That was included in my mind under functions that are useful in analysis. So let's see how it's stated. Right. So the main theorem, continuity theorem. Theorem 12.12 in the lecture notes. So if f partial function on the reals is computable, then f is continuous on its domain as a function from real numbers. So let's expand that out, i.e. all x in the domain of F all epsilon greater than 0 exists at delta greater than 0 such that for all x prime in the domain of F, if x prime minus x, if x prime is within delta of x, then f of x prime is within epsilon of f of x. Okay, so that is what we're going to prove. All right, so the time is now 1 minute past 4 according to the clock on the back wall, so we'll start again at, well, let's start again at quarter past.
One question.
Yeah.
Why do we need to find periodic rationals? Can we just use like decimal expansion and then separate the number like first and decimal digits, and then we separate it by semicolon and then write one?
Yeah, so we could indeed, we could do the same thing with finite sequences of decimal digits instead, but it's a bit mathematically less natural to consider. Then you're representing those rational numbers that can be written as a fraction with a power of 10 as denominator. So you can do that, and you get an equivalent representation of the real numbers. Yeah, so you can do that. But you know, your alphabets are bigger, and it seems more natural to me to work with dyadic rationals. But anyway, good question. You can also work with arbitrary rational numbers and give them representations of pairs of integers. That would also work. Other questions? Okay, well, we'll still start again at quarter past. Okay, so basically the last part of the lecture is going to be to talk about this continuity theorem. Firstly, a little bit about how one applies it, and that part's not in the LaTeX lecture notes. And secondly, its proof. Just to say, we already had a continuity theorem 2 lectures ago. Last lecture for computability with omega words. And there we showed that functions that are computable on omega words are continuous with respect to the topology on the space of omega words. Here it's a more subtle result because we're talking about here the computability of functions on the reals, and such a function is computed via a function on omega words that does the computation. And the property of continuity we're establishing is the usual notion of continuity for real value for functions on the real numbers. Specialized to the case of partial functions, and this is stating continuous with respect to the subspace topology on the domain of definition of a partial function. It is just the usual, you just write down the usual condition for continuity, making sure that you're always quantifying over elements in the domain of a function when you have a partial function. So I just want to talk a little bit about how one applies this. So firstly, it is it's property, every computable function is continuous. It's not an if and only if. So there do exist continuous functions that are not computable. However, it's very hard to come up with examples of such things because in some sense, continuity is basically equivalent to computability in that if one can strengthen the notion of continuity with what one might call effectively continuous by making sure that somehow there's some computability content in how one computes the delta from an epsilon and things like this. I'm not going to make it precise. And if one states the notion of the stronger property of effectively continuous, it turns out in the appropriate way, every computable function is actually effectively continuous, and every effectively continuous function is computable. Another way of looking at it is from an appropriate constructive viewpoint, one can make it consistent that every continuous function is computable. So anyway, it's hard to give counterexamples of continuous functions that are not computable. On the other hand, what we do have is continuity is a necessary property for computability. So it's now easy to give some examples of functions that are not computable. And actually, this is a function that is often used in analysis. So unfortunately, well, I mean, it is just a fact of life, a function that is not computable is the sine function on real numbers. So the function, not sin, not sine as in the sinus, but it's the sine, sine, that function, sine function, SGN from reals to reals, is of course defined by sine of x is 1, say, returns minus 1, 0, 1 according to x is positive, x is negative, x equals 0. And that is, of course, a very non-continuous function at 0, so is not computable because not computable. The one other example I want to do, just so you're aware of how to be careful with such things. But let's consider what about the reciprocal function? X maps to 1 over x to the minus 1. As you know, draw a graph of the reciprocal function that's like this. So does anyone have an idea whether this function is computable or not? Yes?
I think on its domain, yes.
Okay, very good.
So without 0.
Yeah. So indeed, it is computable. And essentially, one can work that out by writing an algorithm for 1 over x on dyadic rationals. But if you've got a dyadic rational, 1 over the dyadic rational is not necessarily a dyadic rational. It's a rational, but it's not dyadic. But you do a 1 over x to within a sufficiently close epsilon on dyadic rationals, and then you work out how far you need to go in order to start approximating at the right rate of convergence. And it can be done. It's a little bit fiddly. I used to set an exercise on this in times past. So it is indeed computable. But I wanted to raise this as an example because sometimes people are mistakenly under the impression that 1 over x is not a continuous function, but it is continuous on its domain of definition. So there are all sorts of nonsense YouTube videos that say this is an example of a non-continuous function because it's not continuous at 0. It's not even defined at 0. I mean, but that's the anyway. So just to be careful. So the reciprocal function is computable, but we can't infer that from the fact it's continuous. But it is continuous, and that doesn't contradict. So there's no contradiction. Right. So the remainder of what I want to do today, I don't know if it will take the full hour, we'll see, but it does require a bit of work, is to prove the continuity theorem, which I'll leave up in this form. To do so, we're going to have a useful little technical notion. We know what the names of a real number look like. But it's going to be useful to consider particularly nice names for a real number. So we say a name P, which is, so all names are of this form, so on, is called close in the notes. It's close if for every n greater than equal to 0, if we consider the nth approximating dyadic rational, and we consider how far it is from the real number represented by P. We had a lemma saying that this is always within 2 to the minus, this is always less than or equal to 2 to the minus n. The name is close if it's always within 2 to the minus n plus 1. Okay, so the approximation is twice as good as it needs to be. Okay. And the simple proposition is, or lemma, is that every x in, so the first point is every x in the reals has a close name. And secondly, well, actually, before we do that, how can we show every x has a close name? Can someone see immediately how to do that?
Just an idea, not we just miss out the terms of the sequence out.
Yeah, indeed. So we've seen that every real has a name. We take the name. Actually, all we need to do, we take the original name that we find for it. We just need to leave out U0, and then everything's shifted by 1, and that's a close name. Okay, you can work out the details for yourself, but that's where you need to be. The second, and really the point for considering the close names, is this property, which doesn't hold for arbitrary names, which is that if U0, U1, U2, and so on is a close name for x, then for every n greater than or equal to 0, every x prime whose distance from x is strictly less than 2 to the minus n plus 1 has a name of the form U0, U1, up to, we keep the first n terms, and then we carry on with some different dyadic rationals here. So with a close name, once we've got past the nth term, we know we're within 2 to the minus n plus 1 of the real number itself. But moreover, every other real number that's within 2 to the minus n plus 1 to the real, we can approximate by continuing the name, sticking with the same prefix that we used so far. But this does not hold for arbitrary names. And the proof is in the notes. It's only 3 lines, and it's basically just an application of the triangle. So I think I just won't prove the lemma at all, but you've got the notes, see the details, or you can think about it for yourself, and you'll see that it's not hard to prove. The other thing to think about is why this property doesn't hold if you don't have a close name. So in general, for an arbitrary name, this property does not hold. And it's kind of, if you're approximating numbers, dyadic rationals that are as far away as possible as they can be within the scope of the name from the limit real, then if you consider a real that's this far from the limit real in the opposite direction from the approximations, then you won't be able to continue approximations. You can think about it. And the other point to mention is, in the end, we end up with the name of this form, but the name we end up with is not itself a close name. Okay. Right, so we're going to prove the theorem. So we suppose f is computable. That means it's got oh yeah, that's all right. I haven't written on that panel board yet. The proof of the theorem. So suppose that f is computable, that means, by the definition of computability with respect to a representation, f has a realizer G that computes on omega planes. So suppose let G on words of the Cauchy alphabet be a realizer. And we want to prove this property here that for any x in the domain and for any epsilon that exists at delta, blah, blah, blah. So suppose x is in the domain of f. Suppose epsilon is greater than an arbitrary value greater than 0. And we need to find delta we must find delta greater than 0 such that, let's call this property here for all x prime in the domain of f. If x prime is within delta of x, then f of x prime is within epsilon f x prime. Let's call this star. Okay, and if you want to show it star. We're going to use the continuity theorem. So the point is we're going to get the continuity of the real function f as a consequence of the continuity of the omega word function g. So to do that, we're going to apply the continuity of g to a particular element in its domain, and that element will be a name for x, but so that the argument works, we pick a close name for x. And that's why we introduced the notion of close names so that this argument will work. Well, sorry, so that this argument will work. So let P be a close name for x. And we'll again have this P in the canonical form of U0, U1, U2. So these are all finite words representing dyadic rationals. Close name x. And now, so P is a name for an element X that's in the domain of F. Therefore, because G realizes F, G will be defined on P. So let R to define R to be equal to what we get by applying the function G. So we compute it by R, like to Turing machine to the name P. So, which is defined because and because G is a realizer for F, R is a name for F of X. Because G realizes F, R is a name. And since R is a name, then R is of, so therefore, R itself, it's a name for a real number, has the form of, again, a sequence of approximations and a sequence of finite words representing dyadic rationals. So that's right, these for these. So R is these, first the first word for dyadic rational approximation, then V1, then V2, then V3, so on. Point is we're trying to find the delta, yeah. And we want to find a delta such that whenever we consider a name for something within delta of X, then we apply F to it, or equivalently G to it, we'll get, or G to the name, we'll get a name for something within epsilon of F of X. Okay. So what we're going to do is we're going to, so here this is a name for F of X, and we're going to look at names that are guaranteed for other elements here that are guaranteed to be within epsilon 2 of this. So we're going to look at a prefix of this that if we have a name starting with that, we're guaranteed to be within epsilon 2 of F of X. So we're going to say that N be how far we want to look along here, so that N be such that define some number N such that 2 to the minus N is less than epsilon over 2. So this is one of these argument, analysis-like arguments where an epsilon over 2 is the right thing to consider. So then, because this is a name, we have, if we consider dyadic rational represented by V of this capital N, and this is a name for F of X. So the distance of this from F of X is by proposition 12.8, which I had earlier, which says the nth term is always within 1 over 2 to the minus n of the limit. So here we've got the limit, here we've got the capital nth term. So this is within 1 over 2 to the minus 1 over 2 to the n. So this is within 2 to the minus. This is less than equal to 2 to the minus n, and that's less than epsilon over 2. So this inequality was by proposition 12.8, which we had earlier. The simple proposition immediately after the definition of the representation that the first point was every realized representation, and the second was every approximating dyadic rational if position n is within 2 to the minus n. Right.
So let's go on to another panel. Part one through. So we go on to page 2. And what we're going to do is we're going to consider the prefix of R that consists of the first n terms here, and consider how many symbols are in that. It's an omega word, sorry, it's a prefix, it's a finite word, so it has a certain number of symbols, n, let's say. So let n be the length, well, let's just use the symbol, the length of the prefix v0 up to Vn, prefix of R, length of this prefix of R, with the semicolon afterwards. And by the continuity theorem that we had last time, this is the output of our function g, and the continuity theorem we had last time said the finite amount of output was determined by the finite amount of input. So there exists some n such that every n-length prefix of p will give us the same n first n characters of output. So there exists so by last week's continuity theorem, there exists an n greater than or equal to 0 such that p prime in the domain of G, if p prime agrees with p on the first n characters, so if p prime starts off with the first m characters, this is m's here, for p, then g of p prime, we apply the function g to it, it behaves on p prime just like it behaves on p, as far as the first little n characters. So in other words, if we restrict this to n, we'll get the same output for the first little n characters, which is again v0 all the way up to v sub n with its semicolon. Okay, so we've got some little m prefix, so prefix length of p that will guarantee that we get v0 up to v whatever it was. The guarantee that we get the first n I'd like to find n. Yeah, yeah. So we've got the same n symbols in p prime, we get the same first n. This should be capital N. Right. First, so we get the same first capital N approximating their different rationals in the output. So let's let m prime. So the problem with the little m is that it's some prefix of p, but maybe it stops in the middle of one of these words here. So let's kind of normalize things by taking a slightly bigger m prime. So let n
greater than or equal to 0 be such that the prefix of u zeros up to um with the semicolon afterwards of p has length some n prime greater than or equal to n. And we can take n to be the smallest such number. So we basically want to consider the prefix of p that consists of a whole number of words and semicolons, words approximating dyadic rationals, whose length is at least little n, so that if we consider any real representative name starting with that prefix, we're going to get back the same initial prefix of v zeros as far as v sub n. So then for all p prime in the domain G, p prime restricted to n prime is also so if p prime restricted to n prime is the same initial prefix u0 of p up to u sub n, then because that's a special case that we've got even longer prefixes here, then it certainly holds that G of p prime restricted to n greater than little n. Yeah, u0 up to n. So again, this prefix approximating f of x. Okay, so now for the last step, we're going to use the property now of x, the fact that p is a close name. And we're going to use this property that when you have a close name, everything within an interval around the real number represented by the close name can be represented by starting with the same prefix as for the close name and then extending. We're going to use that property, which unfortunately I'm probably going to have to run out before we use it. I was trying to avoid that, but such is space, and I do want to keep the statement of the theorem on the board. So define delta. So we wanted to find delta. That's what we're aiming to do. So finally, we're going to define our delta. Our delta is 2 to the minus n plus 1. And we need to show star holds, namely for all x prime in the domain of f, if x prime is within x of delta, then the f of x prime is within epsilon of f of x. So to show star, suppose x prime is in the domain of f, and x minus x prime, the distance of x from x prime is less than 2 to the minus n plus 1, less than delta. Okay, good. So now we can use our property of the close name here with our n is m, and for any such x prime that's within 2 to the minus n plus 1 of x, we can use the fact that p is a close name of x in order to find a name for x prime that starts off with u0 up to u of capital N here, and capital N here, and then continues with something else. So by the close name, so because P is a close name for x,
for x, then there exists a name for x prime of the form u0 up to u sub n, and then continuing with some other stuff. U prime n plus 1, U prime n plus 2, and so on. And as I say, so the proof has got to this point, it would be nice to be using a different colour, and we simply use this property 2 here of a closed name that I'm about to rub off. This is by the property of closed names we established there. And now we see since x prime is in the domain of P of F, sorry, we have a G is a, so that means this is P prime, the name for x prime. We have that G of P prime is defined because it must be a name. The G of P prime is a name for f of x prime. And moreover, because G of P prime has the nth prefix like this, sorry, because P prime restricted to n prime, because P prime has the u0 to u capital N prefix, P prime restricted to n prime looks like this, and therefore by this implication, G of P prime restricted to n. So let's call this star star. So by star star, G of P prime restricted to n is E0 up to Bn. And that means that G of P prime, so this is within 1 over 2 to the n of the, this is within 1 over 2 to the n of the, of x prime, because this is the name for f of x prime, and by our rate of approximation of names, we have the distance of G and distance of this, the rational B of n minus, this is a name for f of x prime, so the distance of that from f of x prime is less than or equal to 2 minus n, which is less than epsilon over 2. Okay. So here we have the distance of f of x from the rational, from the dielectric rational B of n is less than epsilon over 2. And the distance of f of x prime for the dielectric rational of V of n is less than epsilon over 2. So putting those two together, the distance of f of x prime from f of x is less than epsilon. So combining
put them in orange bubbles. So combining this and this. Combining two orange bubbles. That's f of x. And set of x prime, the distance between f of x and x prime is less than epsilon. And that's exactly what we needed to show. Okay, so we're done. Good. That was quite a technical end to the last bit of the lecture. But now we can have a break for 3 weeks. So I wish you all a very happy Christmas and successful New Year. New Year too. And I'll see you again for those who wanted to do the advanced material. See you again in 3 weeks' time. Any questions? No, good. So have a very pleasant holidays.